Alright, let's look into section 8.8. This section is going to cover covalent bond energies and chemical reactions with primarily covalent compounds. We talked a little bit about previously ionic compounds and the bond energies that are required to form ionic bonds. Now we'll take a look at just specifically those covalent bond energies. To break bonds, anytime we break a bond, energy has got to be added to a system. So when you got an oxygen molecule floating around in the air, in order to break the bond between both oxygen atoms, you got to add a little energy. So that particular process is always going to be endothermic. When those atoms then reform into something new, so if we've got methane adding to the oxygen to form carbon dioxide and water, that process is going to be exothermic. And since we're always kind of concerned with the amount of energy that is produced throughout a chemical reaction to see if that reaction is going to be favorable or not, see if it's going to be easy to run, and see if it's going to release heat, which is kind of the purpose of burning methane, releasing heat, we want to know how much energy is transferred when we break and form these bonds. So there's a table that's been developed that gives you some very common average bond energies. In your textbook, this is on page 351, and on a test that'll be coming up, not till January 10th, but on the test, if I'm asking you to calculate the energy released from the breakage of bonds, you're going to have a page like this. Now, if you'll notice, there's something different between this particular table and the table that we talked about in the thermochemistry unit. In the thermochemistry unit, you had a table on the back of the book. It said delta HF, and you had a bunch of different compounds back there, like ethene or methane, and it told you the amount of heat of formation for that particular compound. So that was, if you had just carbon and hydrogen, and you combine those two to make methane, how much energy would be released or absorbed to make that particular compound. That's different from this table. This table is looking simply at the amount of energy required to break each of the bond. So for instance, in order to break a hydrogen-hydrogen bond, you've got to have 432 kilojoules per mole of hydrogen-hydrogen to be able to break all those bonds. Okay? So if we're thinking about oxygen, if we come over to the right side of the table, right there, in order to break 1 mole of oxygen, we need 495 kilojoules. So you'll never have to worry about memorizing any of these. All these numbers would be given to you on a test if needed. All right. Looks like my text is up high a little bit here. We're going to look at different types of bond energies that are required to break certain bonds. Here's the hydrogen that we referred to. Here's the chlorine gas. You'll notice that there's less energy needed to break that particular bond. I'm wondering if you can guess as to why that is. Think about the size of the atoms, right? Let's go into HCl. Okay, 427 kilojoules needed there. Again, think about the proximity between the valence electron shells and the nuclei. And then look at oxygen. Boy, oxygen's up there, 495 kilojoules. Well, let's take a look at the oxygen molecule. First of all, the oxygen molecule has this thing in between both atoms. This is called a double bond. It just simply means that there are 4 electrons shared between each oxygen atom. 4 electrons. Okay. And if we can even go to the more extreme, we've got the nitrogen molecule. And look at there. Ooh, there we've got a triple bond. Okay, we've got a triple bond right there. So that simply means that there are 6 electrons shared between each atom. And if you look at the corresponding energy required to break that bond, look at this in nitrogen. 943 kilojoules required to break apart 2 nitrogen atoms. Now, what do we know about nitrogen? If you can remember, it's pretty stable. In fact, when you're doing very, very touchy chemical reactions that are affected by air, you can run these chemical reactions in what's called a glove box. Interesting little apparatus, which is kind of like a laboratory inside of a box, and it's got gloves that you stick your hands into. And we evacuate that chamber, that glove box, of all the oxygen and all the air, and we pump in this stuff right here, the nitrogen. because the nitrogen is so downstable it won't react with anything. Okay? So here's the common trend. For bond energies, single bonds have lower bond energies than double bonds, and double bonds have lower bond energies than triple bonds. So can we do some mathematical processes with these? Well, sure, we certainly can. One other thing, though, that I want to talk about before we do a little bit of math is just quickly let's look at the bond lengths for these different types of bonds. As you can probably imagine, the bond length between two atoms that are singly bonded is pretty long. Think about you and a buddy holding hands, just one hand, okay, and you're stretching each other out as far as possible. So you'd be far away from each other, your heads would be far away from each other, and it would take not a lot of energy to break the two of you apart. On the other hand, if you went ahead and you grabbed two hands, you'd probably come a little bit closer together, and the energy required to break you apart is going to be higher. And thirdly, if you were trying to really glom onto each other, really connect with each other, you may form a triple bond and like hook a leg or something. I don't know. And there you see that the bond energy is considerably more, and the length between the two of you is going to be considerably less. So we can say that the bond length and the bond energy are inversely proportional to one another, right? As one goes up, the other one goes down. Inversely proportional. Okay, now, as I promised, a little bit of math. So if we want to calculate the bond energy in a particular chemical reaction, we need to look at the amount of bonds broken, the energy associated with those breakages, and the amount of bonds formed, and the energy associated with those formations. So this is kind of our Hess's law equation for this particular chapter. Delta H equals the sum of the blah of bonds broken minus the sum of the blah of bonds formed, where blah, D, represents the bond energy per mole of bonds. And you'll notice that moles is stuck in here too. Remember, moles is N. Okay? So essentially what we're thinking about, and we're going to do an example problem here in a second, is if we have some hydrogen gas, getting ahead of myself here. If we have some hydrogen gas right here and some chlorine gas right here, what's the energy going to be to break that guy and break that guy and then have these guys reform with each other to form this, and these guys reform with each other to form this? And that's our overall question. We can look at the same thing for water too, right? Okay, now here's water. What's going to be the big difference? This guy, right? That big guy right there, that double bond. Okay, it's going to take more energy to bust that baby apart. Okay? All right. Here we go. So we're going to use these bond energies to calculate the enthalpy change for this particular process. Now, let's think about something first. We need to know the type of bonds broken, the number of bonds broken for that particular type, the bond energy for that breakage, and we're going to get that from the table, and the total energy change. So total energy change and bond energy are different because bond energy is dependent upon the number of moles. All right. So type of bond broken. HH. Well, there's only one of those. Okay. Where's that come from? Well, that's right here. There's only one HH. Okay. You look at the coefficients, and the coefficient is a 1. So this is a 1. Okay. It's 432 kilojoules to break one of those. That's from the table. That's from the table. And since I only have one of those, that number is going to be the same. Again, I only have one FF. Okay, one FF, 1 mole of that. 154 kilojoules to break that baby apart. Again, we are seeing that FF is a lower energy than HH. Again, I'm wondering if you can understand why. And so the energy change is equal to the bond energy. All right, now let's look at the types of bonds formed. We have 2 HFs formed. Okay, 2 HFs formed. So the bond energy for 1 HF is 565. We'll need to multiply that by 2 to get a total of 1130. Okay, and our overall reaction is going to then take the bonds broken minus the bonds formed, and you're going to get an overall number at the end of the day that comes out to negative 544 kilojoules of energy that should be released. There you go. Pretty cool stuff. If you look in the back of the book, I actually believe that delta H of formation for 2 moles of HF is actually negative 542. So they're pretty darn close, 544 and negative 542. Pretty close stuff. All right, I do have an exercise for you maybe to do on your own. Okay, so we've got this compound right here, CH3N double bond, or triple bond C rather, and that's bonded to, or that's broken up and changed into CH3C triple bond N. So you can see there's a rearrangement. And we want the following information. There we go. So let me show you what this compound actually looks like. That's going to help you. I'm going to just go back so I can give myself some space. Okay, we have CH3 triple bond N, so we're going to have a carbon, 3 hydrogens around it. Okay, and then N. See? Okay. And that is being broken up, and we are getting something out the back side that will look like this. And that's going to form, sorry, that will not be a triple bond. Go back, and let's go here, and let's go there. Okay? So we got to break every single one of the bonds. Break that one, and 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 then form that one, and that one, and that one, and that one, and that one. It'll be kind of easy because you only have 1 mole of each, right? But remember, you have 3 times that you got to break a carbon, hydrogen, carbon, hydrogen, carbon, hydrogen. 3 times carbon, hydrogen, carbon, hydrogen, carbon, hydrogen. All right, see if you can calculate that out and see what you get for an answer. Oh, what the heck, I'll give you the final number to see if you can check your work. I believe it's going to be negative 42 kilojoules. There you go. All right, so you'll notice on the post I give you a little idea as to what's ahead of us. Have a happy holidays. Hope you get a lot of stuff from Santa, and we'll see you in January.